Okay, hello everyone. We're at the beginning of chapter 10 in our book, but we're actually, I think I've mentioned this in class, using another book for this. So we just spent a little review assignment in class going over sequences. So whether a sequence converges or diverges. This chapter is the study of series. So you did a little bit with series back in Algebra 2 Honors. A series basically is very simply the sum of a sequence. So you take a bunch of terms and you add them up. What we did in the last homework assignment was just look at the terms themselves, and we tried to see where the terms were approaching. Were they approaching a number? Were they not approaching a number? What we're going to do in this chapter is study whether series converge or diverge. So all of our series will be infinite. First of all, they're going to go, infinitely many terms, which we kind of have to do because if there was a finite number of terms, they'd all converge to whatever they add up to. We just add them up and that'd be done. So we're going to add up these infinitely many terms and see if they add up to something. Sometimes they'll add up to a number. Sometimes they'll add up to infinity. Okay, adding up to infinity is not exactly what we call it, but we will call it diverges, right? Convergent means approaches some sum. Divergent means it goes to infinity, right? So this whole chapter is studying these series. So it's the first section today. It's kind of just like an introduction, kind of little stuff. And then we're going to develop rules as we go along, okay? So these are just a couple ways to determine if an infinite amount of terms adds up to something. You did this in geometric series, by the way, back in Algebra 200, which you're going to see here in 10 minutes or so. So it's not completely new, but we're going to do this for all series. So little definition first, the kth partial sum. The kth partial sum is just adding up the first k term. So if I say, hey, I want the eighth partial sum, I add up the first 8 terms of this series, okay? What we're going to do as one method, this is just one method. You're going to learn about 7 or 8 methods during this chapter to try to determine if something converges or not. This is probably the worst method of all. It's kind of cool, but it doesn't work very often. So we're going to have to kind of force it a little bit. So what we're going to do is we're going to take like the first partial sum, then we're going to take the second partial sum, then we're going to take the third partial sum. And what we're going to do is we're going to generate a sequence of these partial sums. So we're going to see the first one, the second one, the third one. We're looking for a pattern. And then as we look for that pattern, if we can see the pattern, we'll know whether the series converges or not. So the definition here is, a series converges if the sequence of partial sums converges. Otherwise, it diverges. So we're going to look at those partial sums and see if they converge to something, just like we did in the last section, because then they would be terms instead of sums. So here's an example. By the way, I'm going to refer to a lot of things in this in this chapter by example or theorem numbers. And the reason I'm going to do that is because a lot of times in the book or in the worksheets that you get for homework, the homework will say, hey, you used example 1 to do this problem. So I want to just know how they're labeled when you see them. So this is a series 1 over n times n plus 1. So what we're going to do is look, does this series converge? And what I mean by that, again, is we're adding these up from the first term to infinitely many terms, okay? So we're going to just add up infinitely many of these terms. A lot of times, by the way, we don't write this here. We just leave it blank because we just know in this chapter we're working with infinite series, so it's kind of always something to infinity. Sometimes we don't start with 1. We could start with anything we want, which we'll talk about also in a second. So here's what we're going to do using the method of partial sums. We're going to add up the partial sums. So we're just going to find the first term. The first term is what you get when you plug 1 into this, which is 1 over 1 times 2 or 1/2. The second term is actually 1/6, which you get when you plug 2 in there. It's 1 over 2 times 3, or 1/6. So now we're going to add those together, right? This is a partial sum. So what you see here on the screen is me adding those first 2 terms together, and I got 2/3. Then I'm going to find that third term, which is plugging in 3. So it's 1 over 3 times 4, which is 1/12. We're going to add all those terms together, and we're going to get 3/4. So what we're going to do is we're just going to look for a pattern. There's a nice, clear, obvious pattern. I hope you can tell what the next term is. It's 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6, so on, right? So what we're going to do is we're going to look at that pattern that's being generated here, ... and generalize it. Okay, so notice the first partial sum is 1 over 2, the second partial sum is 2 over 3, the third partial sum is 3 over 4. So the nth partial sum is always n over n plus 1. If right now I asked you to add up the first 100 terms, okay, it would be 100 over 101. Boom, got it. Okay. So then what we do, because now we have a sequence, is we find the limit of those partial sums. Because whatever the limit of those partial sums is going to be the limit of my series. If it's not infinity, even if it is infinity, but if it's not infinity, it's a number. Okay. So what does it equal? Well, so we just go limit. Let me write it up here for you. Sorry. Limit. Oops, it's going to be our limit. As n approaches infinity of n over n plus 1. It's just higher power rule, or it's infinity over infinity. You could take derivatives, but it's equal to 1. So that means all of these terms, infinitely many terms, add up to 1. They don't really add up to 1. We say it converges to 1. That's the terminology I use right here, right? The sequence of partial sums converge. Therefore, the series, converges, and it converges to 1. We might just say it adds up to 1. It doesn't really add up to 1. It just gets closer and closer and closer and closer to 1. Okay, so if I generalize that for this one, that's the method of partial sums. Like I said, it's not a great method because we have to find a problem that you can find that pattern. If I just made up a problem right now, you never see a pattern in those partial sums. You could do it, but you never see a pattern. Okay, so what we just showed is the sum of 1 over n times n plus 1 is equal to 1. This actually has a name. It's called a telescoping series. It's super important. It's one we use a lot in this class. As we develop series and learn whether they converge or diverge, we want to keep using them to use against other series. So in other words, we do a lot of comparisons in this chapter. You compare one series to another. So if you know what's happening with one series, it can be pretty useful. So that's called the telescoping series. All right, I'm just going to show you another example real quick. -1 to the n minus 1. And we're just going to use the same method. The first term is 1. I'm going to go through this quickly if that's right. The next one is 1 plus -1, which is 0. The next one is 1. The next one is 0. So it just bounces back and forth from 1 to 0 to 1 to 0 to 1 to 0, which means it does not converge to anything because it's not all approaching the same number. Okay. So again, not the greatest method. You'd probably never use this method unless someone told you. So ultimately in this chapter, we're going to have to decide which methods to use. But this method, someone would have to tell you to use this method. It's not a method you'd ever kind of use on your own. All right, next one. Usually I would do a proof for this, but I'm not gonna. So I'm just going to tell you. This is actually example 3, just so you know. This is called a harmonic series. Okay, very important name. I'm going to refer to harmonic series all through this chapter. It's the series of 1 over n. So in other words, it's 1 plus 1/2 plus 1/3 plus 1/4. It turns out this one diverges. You can't actually see that in the partial sum. You can't do a partial sum of this. If we have time in class, I might tell you why this diverges. At this point, just kind of believe me and say it does diverge. Okay, so that's example 3. And this next one is theorem 8.15. This is the old one you've done before. This is a geometric series. You did this in Algebra 2 honors. It's any series that's formed by multiplying the terms over and over and over by a certain number. So it's called a common ratio. I don't know if you remember that. R is the common ratio. Okay, and this geometric series will converge if the absolute value of r is less than 1. If r is a fraction in essence, anything between -1 and 1, this will actually converge. Okay, if it's bigger than 1, it will diverge. And that might be obvious because if it's bigger than 1, that means the numbers are going to continue to get bigger, which means if you keep adding bigger and bigger and bigger numbers up, it's not going to converge. It's going to diverge to infinity. Okay. It also turns out, you may or may not remember this from Algebra 2, probably not, it was a long time ago. We can actually figure out what it converges to. It always converges to that little formula here. I'm not going to prove that to you again. You proved it in Algebra 2 honors just to save some time in the video here. I'm just going to tell you that it converges to the first term, a sub 1 over 1 minus the common ratio. We're going to do an example problem in just a second where we try to see if something converges or not and then what it converges to. So we're going to develop a bunch of tests in this chapter. So the first test that we're going to do is called the nth term test. You do need to know these tests by name. And we're going to talk about how to solve them. So here's the idea. We're trying to determine if a series converges or not. So think about a series, I don't know, that just looks like this, n, which is 1 plus 2 plus 3 plus 4 plus dot, dot, dot. Okay, versus maybe the 1 over n, which is 1 plus 1 half plus 1 third plus 1 fourth plus dot, dot, dot. So the idea of the nth term test is if a series is going to converge, the terms have to be getting smaller. Okay, remember we're adding up infinitely many terms, right? So if the terms are getting bigger and bigger and bigger and bigger and bigger, it's not going to converge, right? It's just going to get, the sum is going to get bigger and bigger and bigger and bigger and bigger. It's going to go to infinity. However, if the terms are getting smaller and smaller and smaller, it might converge. Not for sure, but it might. And not only do they have to be getting smaller, they have to be getting smaller and approaching zero. Because if they were getting smaller and let's say approaching 2 or something like that, then we'd be ultimately adding up a bunch of 2's, infinitely many 2's, which again is still going to add up to infinity. So the nth term test says this. It says if the limit as n approaches infinity of a sub n does not equal 0. So these, what I'm referring to right now, are the terms. Notice there's no summation there, right? No summation, it's just the terms. So if the terms are not approaching 0, if they're getting bigger or they're approaching 2 or something like that, then the series has to diverge. It's a quick, easy test. It's the easiest test there is, actually, that you just look at the terms. If you think about the in-class assignment we did, or I'm sorry, the last homework we did that we went over in class with all those sequences, any of those sequences that we turn into series can only converge if the terms are approaching 0. If they're not approaching 0, it's going to diverge. However, it's not the case that if they approach 0, it does converge. It might converge, right? So we have to do some other test. So if the terms approach 0, we have to do another test. Excuse me. If they don't approach 0, then they diverge. If they all converge that approach 0, our life would be really easy. We just do this and we'd be done for every problem. It doesn't work that way. We're going to study that a little bit more as we go through this chapter to see why that's true. So there's just a bunch of examples here. I can do these all really super quickly. Whoops, don't worry about that theorem 8.19 yet. Okay, so what I'm going to do, so these are all series, and I'm going to see if they converge or not, right? So what I'm going to do is just think about them as terms. So in other words, let's do this one here, right? The limit as n approaches infinity of n over 2n plus 1. That's a higher power rule. That equals 1 half, which is not 0, yeah? Therefore, that one we know diverges. We would be done with that test. The nth term test is the best test. It's the easiest one, if it works. It doesn't often work, but if it works, gives you not equal to 0, then you're good. This one, higher powers in the bottom, that equals 0. So that means further investigation is needed. This one, higher power in the bottom, equals 0. Further investigation would be needed. We need another test, which we'll do. We'll learn those as we go through the chapter. And then this one, let's just write this one out. Limit as n approaches infinity of e sub n over n. This is infinity over infinity right now, so I'd have to take a derivative, which is e to the n over 1. And now e to the infinity is still infinity, which is not 0. Therefore, it diverges. We're going to talk about these tests and how we write them up as we go through the chapter also, because there's like a formal language for it. All right. All right, now that theorem 8.19 is kind of hiding, here's theorem 8.19. Kind of mentioned this before. Theorem 8.19 says if a sub n and b sub n are both series, and a sub j equals b sub j plus c for every j greater than k, and then both series converge or both diverge. That sounds very confusing. Right? You're like, what the heck is he talking about right now? So I don't really want to worry about that language. I'm just going to tell you what it means. This is called adding or deleting terms. What it means is this. Remember back earlier in the lesson, I told you that 1 over n converged. Whoops, sorry, 1 over n diverged. That would be bad. The harmonic, right? 1 plus 1 half plus 1 third plus 1 fourth. This diverges. But let's say I added a 2 and a 4. I kept the pattern the same. if I added those terms. You can add or delete terms to any series, and it doesn't change whether it diverges or not. Think about this. If this thing diverges, it's headed towards infinity. I can add some terms. It's still going to diverge. But even if I just start a new series, like 1/4 plus 1/5 plus 1/6, this one's going to diverge also, believe it or not. Okay. So just means if you have a pre-existing series and you chop off a bunch of terms, you're not going to change whether it converges or diverges. You will change what it converges to, but you won't change the fact that it converges. Same thing if you add them. Okay. I think I might have an example. Nah, it's not worth that one. So we're going to bump down to this one now, which is theorem 8.2. This is pretty straightforward. It says if a sub n and b sub n are convergent series with sums a and b, then a sub n plus b sub n converges to a plus b, c times a sub n converges to c times a sub n minus b sub n converges to a minus b. I'm going to let you just look at that. I'm not going to say much. It should be pretty obvious. But basically, if I have two things that are added together, I can find the limit of each one and add them together. Or let's say we do this. 2 times n plus 1 over 2. Whoops, sorry. My mistake there. This was the telescoping series. Remember, n times n plus 1 is the telescoping series. Sorry, 1 over. That was bad. Eesh. 1 over n times n is the telescoping series. Multiplying it by 2. Sorry, this got a little messy. Let's try this again. 1 over n times n. We know that this approaches 1, right? Which means this has to approach 2. You can like factor out the 2 in essence, right? Probably something you would think was pretty obvious, but that's theorem 8.2, so you can do that. You won't ever use that theorem, I don't think, by name, but you'll probably use it. All right, so here we go. I said before, this is kind of last example, that we can actually find the sum. So here's the question on this one. It's, does this converge or diverge? And if it converges, what does it converge to? Okay. So I'm going to walk you through this one and tell you how to do it. So this is what we just talked about, right? This is a telescoping series times 7. So this thing has to add to 7. Okay. This is a geometric series. Okay. It's got a first term, plug in 1 to that. 1 minus 1 is 0. 3 to 0 is 1. So it's got a first term of 2 and a common ratio of 1/3. We're changing that 3. We're adding a 3 to the bottom every time. So we're multiplying by 1/3. So remember that formula is a sub 1 over 1 minus r. So we can just add these together. 2 over 2/3. Let's see, which is 7 plus, if I invert and multiply, 2 times 3/2. Is that actually a 10, I guess, yeah? So telescoping series, geometric. There's not very many series, actually, that we're ever going to figure out the sum. Most of the time in this chapter, we're just going to figure out whether or not it converges or diverges, but not the actual sum. But telescoping series we can do, because we've done them. Geometric we can do. Just about done. Just a couple things here that might help. If one series is convergent and the other one's divergent and you add them together, it's going to diverge. It's just like adding a number to infinity. Okay. And then just to kind of come back to that nth term test, just to remind you, this is maybe the most important thing. If a series is convergent, so this is, sorry, not exactly the nth term test, it's just kind of flipping things around, but it says if a series is convergent, then the limit as n approaches infinity, sorry, I got an extra infinity in there. Then let me write it this way. The limit as n approaches infinity of the terms must equal 0. Okay. But not the other way around. Remember, if it's not, okay, meaning that if the limit is 0, it doesn't necessarily mean it's going to converge. It might converge, it might not converge. Okay, but the theorem says if I know that it converges for somehow, then I know the limit of the terms must be 0. However, if the limit of the terms is 0, then it may or may not converge. You're going to see this in the next lesson, or maybe 2 lessons from now. Notice both of these problems. The limit as n approaches infinity of 1 over n is 0. The limit as n approaches in favor of 1 over n squared is also 0. But it turns out one of these converges and one doesn't. We all already know this one diverges, right? That's the harmonic one. It's going to turn out later on that that one's going to converge. We're going to talk about why in another lesson. So it's not quite as simple as saying if the limit is 0, boom, you're done, it converges. However, if you do know it converges, that means the limit must be 0, because if it wasn't 0, it wouldn't have converged in the first place. All right, I know that was a lot. That was the first thing from chapter 10. Hopefully that's enough to get you going on tonight's homework, and we'll move along from here.